what our hospital team is deeply interested in. Okay. So now what I'm going to do is I'm going to go through each one of these issues relative to the protocol. The next one is dark adaptation, and this is part of one of the foundation elements in the circadian design. And I'm going to talk about this a little bit relative to patient experience. Dark adaptation has to do with the kinds of changes that happen in your eye when it's dark. And there's two things. One is you get pupil size changes, and this is something you all know. So if there's very low light conditions, your pupil opens up, lets in more light. When there's very bright light, your pupil gets very small. Okay? The second one, which is what I want to talk about, is the chemical changes that occur in the retina at low light levels. And this has to do with the buildup of rhodopsin in the eye in order to allow you to see at night. And this is one of our big project areas in the circadian field. And to really understand this, the visual process of going out to the beach is very different than the visual process of coming in. And you need to think about this a little bit. So in other words, if I go out to the beach, I'm going from dark to light. I get immediate adaptation. Okay? My pupil stops down, bleach out all the rhodopsin, I can immediately see. But if I go from light to dark, that takes 15, 20 minutes in order to visually adapt. It's a very different visual process. So what happens is when I'm going from light conditions to dark conditions, you build up slowly in the eye rhodopsin, which allows the dark adaptation to occur and allows your rod function to have heightened contrast sensitivity. So your chemicals in your eye build up very slowly. It takes about 20 minutes. Okay. So you get this kind of function here is that you get this sort of very quick response here, but contrast sensitivity maxes out at about 20 minutes. Usually what I do with my students is I turn off all the lights in the room and I let them fumble around in the dark, and then after about 20 minutes they can all see. I won't do that today, but this process takes a long time. Okay? Now this is critically important in healthcare facilities, and it's particularly important on transitions in spaces. If you're going up and down stairs, particularly in healthcare facilities where you've got older people going up and down stairs. Okay? It takes 20 minutes to adapt to this condition, yet you've got a person going down the stairs in 30 seconds. So there's a disconnect there in the design process. Why is this important to you? Okay? Why? Falls are a major cause of death and injury for older people. Okay? Huge issue in healthcare. And our hospitals are absolutely concerned about this. It's like either number 1 or 2 on their list of design priorities. Okay? Trips and falls. Okay? We have an aging demographic. Okay? Our demographic, we're getting older. Okay? And we have visual problems. There's a really a big uptake in sort of elder care facilities. People are very concerned about this. We started experimenting with the circadian design initially in the Circadian house at UC Davis, and this was a zero-net energy house, and it was the first circadian house in California, and this was something I was responsible for the lighting design, and this was basically an energy house. But the idea was to explore circadian design on this, which would help us learn about some of the basic issues and then move these issues into healthcare. So this isn't the most attractive house in the world, but it's the best house in the world to live in because it's all circadian house and it supports wellness. So we got to experiment with a lot of these different issues. I'm not going to go through all the different parameters here. I think the slide presentation is going to be available on my website. so you can download it. Also, I think that they're videotaping this, so you can go through this in more detail. Okay. So in terms of the circadian design, incorporated a lot of daylighting and blue-rich light sources throughout the day. So during the day, lots of light. So it bleaches out the melatonin. The light sources are biased towards the blue end of the spectrum, supports circadian wellness. Whole space, very well daylit, with very blue-white light sources throughout the day, is what you expect. Okay? Towards the evening, we get a progressive reduction in color temperature, and we start migrating towards the red-amber. And also, we bring down the intensity. Again, this is tracking the diurnal variations in spectrum intensity that you would normally see, how our eyes have evolved. Okay, so this kind of shift, sort of showing it simultaneously. Here, this is during the middle of the day, and this is towards late evening. Okay? Now, when we experimented with this, we can all tell the differences between this. But if you ask the occupants, did the lights change? They say no. Okay. You change a little bit throughout the whole day, your eyes don't notice it. Okay. So this is kind of the variation. And again, this supports circadian wellness with the idea that when it's time to go to sleep, you haven't had any blue light disruption on your melatonin. When you wake up in the morning, you've got this kind of light, you bleach out the melatonin, and it resets your balance. Okay. And again, the attempt here was to correlate the spectral distribution of the light source with how your eyes have evolved. Okay. So by doing this, maintains the circadian rhythm, maintains the optimum hormone balance, and maintains sleep and all the other issues. So this was reasonably successful. The dark adaptation part of this was less directed towards the circadian balance and more directed towards preserving dark adaptation at night by non-bleaching of rhodopsin. Okay? And so this is sort of the main focus on this part. Was you've got the impact on the melanopsin receptor. So you don't want any blue lights. But blue lights also have a profound effect on rhodopsin. And rhodopsin is your dark adaptation chemical in your rod function. So what you want is you want lights to support this part, you want them in this end of the spectrum in order to maintain dark adaptation at night. This has to do with trips and falls. I'm not talking about melatonin. I'm talking only about trips and falls. Okay. You've all seen this kind of light. Okay? People put blue light nights in. Okay? This is the worst thing you could do. Okay? This looks really good. Okay? And I tell my students, it's not my bathroom. Okay? But this looks really cool. It's also the worst thing. Not my bathroom. So the idea here is that this kind of light at night, okay, in this region here, does two things. One is it disrupts your melatonin, and you lose your dark adaptation. Now the reality is, this is exactly what we're doing in hospitals today, because there's a very strong blue pump on fluorescence and on LEDs. And this is the worrisome issue, is that this is exactly what we're doing. Okay. So the idea is what to do, okay, for dark adaptation. Well, you don't want to be using it in these regions here. You want to be using the red bias. So I worked with my advisor, Berkeley, who was the gentleman who found the melanopsin receptor. And I said, what to do? What spectrum should I use for bathrooms and hospitals? And he said, use red. Okay. So we built a whole series of bathrooms using red. Okay. Now, why red? You've all seen the submarine movies, right? Where they're in the submarines and they have red light on, right? And the red light, so when they come up top, they can see. Okay? And the reason you use red is it preserves your rhodopsin. Okay? So that's why I started with red. Okay? And the red was furthest away from this. wanted to have something down this end of the spectrum. So we started our bathroom designs with red. Least impact on melatonin suppression. Okay. Not my bathroom. But the red looked terrible. Okay? And so all the science, okay, and all the measurements, really good for dark adaptation. Okay? No melanopsin disruption. So the science was really good. But everybody said, no, we're not going in there. Okay? Okay. And there's something about red that is the Helmholtz color theory has RGB. We have many red sensors, more red sensors than any other sensor. And women have even more red sensors than men. There's probably a good evolutionary argument for that. I mean, we're very biased towards red. But there's something about saturated red light at night which is very frightful. It's very ghoulish. I don't know if ghoulish translates, but it's sort of not good. And in a hospital environment, not good either. Yes. So what we did was we moved up a little bit and we used red amber. Okay? And what we did was we experimented in this home and we put red amber everywhere, all sensor-based, all smart controls. Okay? So the idea is that if you get up at 2 o'clock in the morning to creep around, to go get a drink of water or go to the bathroom, you've got amber-based LEDs that does two things. One is you have no disruption on your melanopsin receptor, zero impact, very low impact. And it also preserves dark adaptation, so there's no trips and falls. So we did quite a bit of work with this in terms of, and the amber was actually something people said, I really liked it, liked the feel. It felt good. People liked the look of it. But it was also very good performance in terms of melatonin, and very good performance in terms of dark adaptation. So we put this everywhere, and all and this is, it's kind of difficult shooting bathrooms at nighttime, taking photographs. But this is a view into the bathroom, and it's all sensor based. So if you wake up at night, sensor will come on, lights will come on. So this is a floor plan of the Honda house, and what I did is I put amber cove all throughout the house, and so that if you were in the bedroom and you wanted to get in the middle of the night, as you moved here, a sensor would turn all the ambers on. If you were going down the hallway would light up, and the stairwell way would light up with red amber. And so this maintained maintained the lack of disruption, also your dark adaptation. This was very, very, very successful. Again, very difficult to take pictures in the middle of the night. Okay? This is kind of how it looks, and so you can navigate the whole home at very low light levels with safety. Now the issue is this: is that typical design, you would turn all the lights on, so you'd see all the way, but when you head back to the bed, you trip and fall. And this is where the trips and falls are happening. And so what we found was that the folks that are 65 and older, they're going to the bathroom more often at night. They turn all the bathroom lights on. Two things happen. They bleach all the rhodopsin in their eyes. So now they're visually blind when they turn the lights off. And number two, they've disrupted their melanopsin receptor and they've lost the melatonin. So now they can't go back to sleep. So it's a two-edged sword here. Okay? So this kind of process was very successful. Okay? So this is kind of showing you sort of the daytime, nighttime view of the bathroom. Is that during normal time at night, if you go into the bathroom, you have this kind of scenario here. At midnight or later, if you go into the bathroom, a sensor would come on and would turn on a low-level amber light. This was of strong interest to the hospital folks because people getting up and going to the bathroom, tripping and falling, and also sleep disruption. So this is something that we moved over into the custody zone.